I think of this presentation as essentially just kind of picking up the random pieces of stereochemistry that we haven't yet talked about. Probably the best way is just to kind of run through this PowerPoint that I stole from a textbook from the past here. It's got a bunch of really good examples of how you can resolve enantiomers. In other words, take one enantiomer and separate it away from its other enantiomer, which is actually a pretty difficult thing to do. And then also today we're going to talk just pretty quickly about things that are chiral without asymmetric carbons, which are pretty weird looking things. So let's get right into it. So the first thing that we have to talk about is this resolution of enantiomers. So keep in mind that definition of a racemate. I'm not sure if I talked about this specifically. I can't actually remember, but a racemic mixture or a racemate is any time you have a perfect 50-50 mix of two different enantiomers, right? Something that is in a solution with its own non-superimposable mirror image. And you should know that a racemic mixture doesn't rotate plane polarized like the pure enantiomer would do. And it has pretty much identical, well, not just pretty much, and absolutely identical melting points, boiling points, and solubility, which means that you have a pretty non-trivial task in front of you if you really want to separate them. And anybody that has, ever taken a drug before or heard anything about drug identification and the importance of enantiopurity in like pharmaceuticals and stuff like that, know how important it is to be able to separate these enantiomers out. So you have to have some way to do that. So one of the things that you can do is recognize that since diastereomers have different physical properties, you can actually take something that is like an already resolved enantiomer, and you can use that to kind of connect it onto whatever those two enantiomers are that you have in a solution. And in that sense, you've essentially made something that used to be just, let's make it simple, right? Let's say that I had an R enantiomer and an S enantiomer. If I use a pure R chemical that will react with those two, what you end up doing transiently is that you make this either RS or RR, and those two things are now diastereomers and they'll have different properties. So that's kind of what we're going to use to interconvert two things. I just wanted to kind of show you a little bit of this. It's not super important that you understand everything right now because it involves a little bit of chemistry we haven't yet talked about. But the resolving agents, these are all some sort of pure enantiomer, right? Very, very, very common that in your, let's say your mixture of two enantiomers in the racemic mixture, there's some sort of carboxylic acid or some sort of group that you can react with. And in this particular case, we're going to take some sort of amine, right, where R is some sort of, enantiopure thing. And we're going to do like this acid-base reaction. And what we end up with is this kind of temporary salt that is a diastereomer with whatever else forms in solution. And then you pick out some sort of property that you'd like to use. Say a really common one is to kind of get one to dissolve and kind of leave the other one behind. And there's a couple of other different things you can do. And so what you'll notice here is that in this particular case, we are taking something which is enantiopure, that tartaric acid. The first enantiomer that was ever separated through some like really excellent microscopic work from Louis Pasteur. You can take some sort of racemic mix of this amine, and you can use that enantiopure tartaric acid to react with your racemic mixture. And then, of course, you've got these two different diastereomeric salts. And in this particular case, you can get one to fall out of methanol and one to kind of leave behind. Then you pour one away from the other, and ta-da! You then go through and get rid of whatever the acid was that you used through some sort of chemical reaction. And then lo and behold, when you're all done, you now have both of those amines separated in two different containers. So, and of course, you could have the opposite of this. You could have an enantiopure amine and react it with a carboxylic acid, or it doesn't have to be an amine and a carboxylic acid. It could be any number of groups that we talk about as, over the next three terms reacting together in some sort of transient way. So it's a pretty brilliant way of doing that. The original experiment to recognize that you could separate one enantiomer away from the other involved literally little tiny tweezers, a microscope, and recognizing like little left-handed spirals from right-handed spirals. And it sounded pretty awful. But this is actually pretty quick. A little more modern way of separating enantiomers involves the use of some sort of chromatographic column. So you can imagine what you do is you take this big giant column that has all of these beads essentially that have some sort of enantiopure chiral compound like connected to them, the little plastics that make them up. And then what you do is you pass a racemic mixture through the column, and then as it kind of flows down this column, due to those transient interactions where one diastereomeric form is a little bit different than another, you can see that you eventually separate out one enantiomer in a little bit of solvent that you can then evaporate and then wait a little while, and then the next enantiomer will come out. So pretty clever ways, and of course now there's all kinds of like high performance ways of doing this with HPLC and among other things. And you'll definitely see those in labs and like biochemistry and such. One other topic that we kind of have to pick up the pieces just a little bit on is this idea that you can actually be chiral without some sort of asymmetric carbon. And so like we don't necessarily need some sort of asymmetric carbon. It's just the most common type, right? I would say that the amount of times that you're going to see something that is chiral without having an asymmetric carbon outside of an organic class is going to be extremely, exceedingly rare. So it is good though to talk about them, and I'm really going to kind of go quickly through this and just show you a couple of examples. Just keep in mind that the chirality, the thing that is absolutely necessary for that, is that you have a non-superimposable mirror image. So the things that we're going to take a look at here are all going to have non-superimposable mirror images. And more importantly, they don't have any asymmetric carbons, right? In fact, right, that carbon right there, that is not asymmetric, right? It's actually bonded to two different groups. If you tried to figure out, one of these sides versus the other in that RNS Conning-Gold prelog system, you wouldn't be able to come up with anything. And so, you can see that there's a site of all kinds of different of stereochemistry. There's 3 different carbon stereocenters in this thing. And really, by definition, if you interchange any 2 groups, that is, in fact, considered a stereocenter. I should mention that the definition of stereocenter is a little bit broader than just like what we see with like asymmetric carbons and chirality and stuff like that. But if you have any questions about what it really means to be a stereocenter, I'd be more than happy to mention it to you. It's just that it's a little bit complicated. So here's just a quick slide of one of the kind of ideas of when I interconvert 2 groups, I end up with some sort of new stereoisomer, and this idea that when I reflect this thing in a mirror plane and end up with its other enantiomer, that you actually end up with two different non-superimposable compounds. One thing that you'll notice in every single non-asymmetric carbon-containing chiral compound, it's always due to some sort of rigid linkage, right? It's something that's going to limit the ability of this thing to rotate around a bond. So like that's what the function of this cyclobutane ring is right here. It just kind of locks it into place relative to that double bond. Other examples of this kind of thing, you can see this thing, which is called a accumulated double bond. It's really common that these guys are chiral, and it almost looks like a propeller. So you kind of lock your propeller in a certain shape due to the overlap of those orthogonal p orbitals. This is a spiro compound, another pretty weird looking structure. This guy right here, this is a biphenyl type of linkage, and it turns out that this thing is kind of locked once again, kind of like a propeller, where like this guy will be in a slightly different plane than this guy due to the interactions of those 2 bromine groups kind of banging into each other and getting locked in place. Another really oddball one that I think is on your homework somewhere, at least this week or maybe next week's is this really strange looking ring. It turns out that if you get big enough in terms of your ring, I think it starts to happen at about 8, you can actually lock yourself into kind of almost like a spiral looking pattern. You can actually end up with trans double bonds within a ring. And so all this is some sort of 8-membered ring that actually has a trans double bond right in the middle of it. Just to kind of pick up a few more pieces here, we're going to end with this. It turns out that if you were to build nitrogen, you would actually recognize that if you use kind of 4 different groups, of course one of those groups is a lone pair of electrons, you would actually notice that you've got some sort of non-superimposable mirror image when you reflected that thing in the mirror plane. But there's a really odd thing that happens with nitrogens, and that is that they actually invert around the lone pair. I often think about lone pairs as very kind of sloshy. So this very next slide is just kind of showing you kind of what happens to that umbrella, right? We've got this trigonal pyramidal geometry. And so if you kind of invert your umbrella, right, you can see here that this form right here that kind of goes, it can go through, it can actually interconvert. Of course, carbons can't do this, but nitrogens can with that lone pair. You're pretty much destroying whatever kind of enantiopurity that you had. And so this kind of interconversion happens pretty easily at room temperatures and pressures. So it turns out that nitrogens like this, or amines specifically, are not able to kind of be enantiopure because of this inversion. It turns out there's some kind of like special things you can do to kind of like trap one form versus the other and turn it into its ammonium salt. But that's a little bit beyond the scheme of this class. So if you have any questions, let me know. I'm sorry I kind of ran through this real quick, but as I said, this is all just kind of like, cleaning up the pieces that we haven't talked about yet that are just good to know. Talk to you soon.